To measure this, we set up in a completely dark room a lamp and the Venus Flytrap with a distance of 0 up to 200 centimeters apart. We only had access to 3 lamps and 3 traps, so we started off with 0, 50, and 100 centimeters for the distance between the plant and the lamp. We did this in 3 separate areas of the dark room. Later on, after 24 hours, we changed the distance of 2 of the lamps compared to the Flytraps to 150 and 200. Now let's take a look at our variables. Our dependent variable is the speed at which the Venus Flytrap closes. Now let's take a look at our independent variable. Our independent variable is what we will be manipulating in this experiment, which is the light intensity. Now for the control variables. In every trial, the same type of lamp was used. Also, the power which the lamp emitted was always 23 watts. The amount of water which was placed in the disc that the pot was on was also always kept constant at 20 milliliters. We also had to make sure that it was always distilled. This is because any water that contains chlorine or any other strong minerals can kill the Venus Flytrap in just a matter of days. The temperature of the room which the experiment was conducted in was also always kept constant. We know this because we checked every hour, and the room was always kept constant at the temperature of 27 degrees Celsius. Also, the time interval between measuring different distances was always kept at 24 hours. This meant that after measuring one distance of the speed at which the trap closes, changing the distance to another 50 centimeter interval, we then left the plant for 24 hours for it to adjust to the light intensity and then measure the speed at which the trap closed. Also, because the room was ventilated, we believe that the oxygen and the carbon dioxide content was always kept constant. And finally, the stick that was used to trigger the plant's trigger hairs was also the same throughout every experiment. From the results obtained after calculating the average speed, we can see that there is a correlation that when there's a decrease in the light intensity, there's also a decrease in the speed at which the Venus Flytrap closes. Even though the results don't differ that much, there still shows a correlation. However, there's an anomaly at 100 centimeters. When the lamp was 100 centimeters away from the Venus Flytrap, the average speed was greater than what it was when the lamp was 50 centimeters away from the Flytrap. This could be due to certain factors that will be explained in the evaluation.
The Venus flytrap, or Dionaea miscipula, is a carnivorous plant native to subtropical wetlands on the east coast of the United States. The plant can live in very poor soil since it supplements its diet with minerals obtained from insects. The speed of closing can vary depending on the amount of humidity, light, size of prey, and general growing conditions. The speed with which trap close can be used as an indicator of a plant's general health. The plant's morphology contains cilia hairs that close over the top of the trap to keep insects from escaping. The glands make digestive fluids and soak up nutrients from prey. When trigger hairs are touched twice in a row within a time frame of 20 seconds, the leaf slams shut and traps the insect. There are also drops of sweet nectars that are found along the edge of the leaf to attract insects.
Now looking at the chemical aspect of this, we have the photosynthesis equation, which is 6CO2 plus 6H2O with sunlight and chlorophyll with 6,6,H12O6 glucose plus 6O2. So the chemical elements in which the Venus flytrap is constructed is principally carbon, oxygen, hydrogen, nitrogen, phosphorus, sulfur, etc. The Venus flytrap produces a vast array of chemical compounds with unique properties which they use to help cope with their environment. Pigments and chlorophyll are used by the plants to absorb and detect light.
So if we apply the concept of physics to this experiment, we focus on two things: the light intensity given from the light bulb within different distances to the flytrap, and the other one is the simple formula of velocity at which the flytrap closes. First of all, the light intensity is calculated by using a formula I, which stands for intensity, equals power over area. The area is basically the surface area of the sphere-like light wave that the light bulb emits, which this is calculated using the formula of 4 pi r squared over 3. The value of r is basically the distance between the light bulb and the Flytrap. So the larger the value of r, the larger the surface area. The larger the value of surface area, the smaller the light intensity. So if we substitute the value of 100 centimeter, 100 centimeter is basically the distance from the lamp to the Venus flytrap. We get 4 multiplied by pi multiplied by 100 squared over 3. And that gives us a value of 41,887.902 centimeters squared to the third decimal point. And if we apply this to the formula of intensity, we get I, which is intensity, equals 23 watt. 23 watt is basically the power which the light bulb gives off over the result that we just calculated, which is 41,887.902. And that gives us a value of 5.491 times 10 to the power negative 4 watt per cm squared. The calculation of the speed at which the Venus flytrap closes is simple. This can be done by using the simple formula of speed or velocity equals displacement over time. Here's a graph that shows the relationship between the light intensity and the speed at which the flytrap closes. Well, theoretically, the relationship should be inversely proportional, but our result does not follow the trend. And this could be due to several factors that affect our results.
Now looking back, when evaluating our experiment, we believe that the results we obtained were quite consistent with 1 or 2 anomalies. However, there are still many things that we could change to increase the accuracy and the reliability of our results if we were to conduct this experiment in the future. First of all, we did not know the humidity in the room. The humidity could have affected the rate of transpiration or the rate of diffusion within the water particles in the air and the plant. This would then in turn may have affected the speed at which the flytrap closes. Secondly, there was parallax error involved in this experiment. When measuring the distance between 2 leaves of a trap, we may not have always measured the distance completely at eye level. Thirdly, as we purchased the 3 traps in this experiment, we do not know if the soil content was kept the same in every single pot. One pot may have more nutrients than another pot. With more nutrients, this would have then increased the speed at which the trap closes. Also, we found after leaving the trap for 24 hours that there was an arachnid inside one of the traps. With an arachnid inside one of the traps, the plant could then gain more nutrients. With more nutrients, it would then be more healthy, which then could have increased the speed at which the trap closes. Also, for every single trial that we conducted, the size of the leaves of the trap may not have been exactly the same in every trial. Traps with bigger leaves may have taken more energy and more time to close than the ones compared to have smaller leaves. This would have then affected the accuracy of our results. So to fix these problems that we faced, in the future, a hygrometer can be placed in the room to measure the humidity so we know that it was kept constant. Secondly, we would buy our own soil knowing the nutrient content in the soil that was kept exactly the same in each 3 pots of the plants that we were using. Thirdly, the Venus flytrap itself would be kept in an enclosed area with nets. This would not allow any type of insect or arachnid to crawl into the plant and give it more nutrients. Finally, in every experiment, it is almost impossible to avoid human parallax error. However, in the future, to obtain more accurate results, when measuring the distance between the 2 leaves of a trap, we could use a string, then mark it down, and then measure the distance of that string marked with a ruler. This would then avoid not reading the distance of the 2 leaves of a trap at different eye levels. To conclude this experiment, we now know that the light intensity does in fact affect the speed at which the Venus flytrap closes. As the light intensity decreases, the speed at which the trap closes also decreases. We have also learned why. We have learned ways in order to achieve more accurate results when conducting this experiment in the future. Also, we have gained more knowledge of plant physiology, especially the Venus flytrap and light intensity, to help us with our future studies. We believe we worked well together, collaboratively, developing our teamwork skills, and combining our ideas to conduct this experiment to produce this clip to share our successful findings. We hope you enjoyed this video. Thank you for watching.